There's a moon in our solar system that refuses to behave like a moon. You look at it once, and something feels off. Not because of its shape, not because of its colors, but because there's a structure running across its middle that doesn't match anything we've seen anywhere else. A ridge that circles the equator almost perfectly, stretching across more than 1,000 kilometers, standing taller than most mountains on Earth. And the strange part is this: nothing about the way moons form should create something like that. Before we get into theories or models, the real question is simple. How does a world this small end up with a feature this precise? And why does it sit exactly where it does, as if someone drew a straight line around the moon and raised it into a wall? This is where the mystery starts. The first step in understanding this moon's wall is looking at what it actually is, not what it reminds us of. The ridge runs and covers most of the equator with only a few broken gaps. Some of the peaks rise close to 20 kilometers above the surrounding surface. We are talking about Iapetus, a moon only 1,470 kilometers in diameter, roughly one-third the size of Earth's moon. Yet it hosts topography that, relative to its low gravity, about 1/44 of Earth's, is proportionally more extreme than almost anything in the inner solar system. On a world this small, that height is extreme. If you placed a mountain like that on Earth, it would stand out immediately. But on a moon where gravity is weaker and the shell is mostly ice, it shouldn't even be stable for long periods. Yet it's still there. The ridge isn't a random chain of peaks scattered around. It follows the equator almost perfectly, like it were placed there with intention. That precision is one of the biggest problems for scientists. Natural mountain belts don't form in straight global lines. They curve, twist, break apart, or diverge. Even when you see long chains on Earth, like the Andes or the Rockies, they follow the movement of plates, not a perfect planetary line. But here, the alignment is so exact that the ridge sticks to the equator with almost no deviation. When you look at the shape of the ridge itself, it becomes even harder to explain. Many of the peaks form clean triangular profiles, with steep sides that meet at sharp crests. A shape like that usually comes from repeated accumulation or erosion under specific conditions, not from deep geological forces breaking through the surface. The width at the base, which averages from 20 to 70 kilometers, the steep slopes, and the uniform cross-section are all signs that something piled material along the equator instead of pushing it up from below. The surface of the ridge is also heavily cratered. This tells us it's ancient. Whatever built it happened early in the moon's history. Crater counts show no signs that the ridge is a recent feature. In fact, the number of impacts suggests it's almost as old as the surrounding terrain. That alone creates another problem. If the ridge formed internally, it would require a young interior that was still warm enough to shift and deform the crust. But if it formed very early and the interior cooled quickly, then internal forces strong enough to build something this large shouldn't have been available for long. The age also matters because it narrows down the options. A younger ridge could be explained by later tectonic stress or some unusual activity in the crust. But an ancient ridge means whatever built it happened at a time when this moon was still forming its identity. It had to be something fast, large-scale, and able to shape the entire equatorial region at once. That's not how icy moons typically behave. So you're left with a structure that is enormous, perfectly aligned, sharply shaped, and extremely old. Every part of it challenges what we expect from natural processes on small, frozen worlds. And this is exactly why the ridge remains one of the most confusing features in the solar system. Iapetus orbits Saturn at an average distance of 3.56 million kilometers, placing it far beyond the bright rings and in the colder outer reaches of the Saturnian system, about 9.5 astronomical units from the Sun, and roughly 1.4 billion kilometers from Earth at typical opposition. Because of this great distance and its small size, surface details were a mystery until the Cassini spacecraft arrived in 2004 and, during a single close flyby in 2007, revealed the ridge in stunning detail. The ridge has been described by planetary scientists as a tough nut to crack, and one of the most astonishing features in the solar system. Before talking about any theories, it's important to understand the world the ridge sits on. One half of this moon is extremely dark, absorbing most of the light that hits it. The other half is bright, covered in cleaner ice that reflects sunlight. This sharp contrast isn't a small feature. It covers entire hemispheres, making the moon look like it was dipped in ink on one side and left untouched on the other. The darker side is called Cassini Regio, and it's a region coated with material that seems to come from outside the moon. The best explanation so far is that dust from outer moons and debris in the Saturn system slowly built up on the leading hemisphere. As the moon moved through this cloud of particles, the dark material settled on the surface. Once that layer formed, it heated more easily under sunlight. The warmth made the ice beneath it sublimate and migrate toward the colder bright side, building an even cleaner surface there, while the dark region stayed dark. This matters because the ridge sits almost entirely across the darker hemisphere. It's not centered between the two sides. It doesn't transition smoothly from one color to the other. Instead, the ridge is strongly tied to Cassini Regio. That placement adds pressure to every model that tries to explain the ridge. If the ridge came from internal forces, why does it align with the dark hemisphere, instead of being evenly distributed around the moon? If it came from external debris, why did the material fall mostly on the darker half? The color split also affects the surface temperature and the strength of the ice. Warmer regions behave differently over long periods. Ice can slump, deform, or slowly move under heat, especially if the crust isn't fully rigid. The ridge stands right in an area where the surface is darker and warmer, which raises questions about how it has held its shape for so long. A feature this tall should show more signs of collapse in regions that heat more easily, yet the ridge remains sharply defined. The two-tone pattern also means that any explanation for the ridge has to consider both the structure and the surface chemistry. You can't treat them as separate mysteries. The dark material changed how the moon evolved thermally, and the ridge sits in the middle of that altered environment. It's not clear whether the ridge formed before the dark coating settled, or whether the coating arrived after the ridge was already there. Both possibilities create challenges. If the ridge formed first, why did the coating follow the equator so precisely? If the coating came first, why would a later geological process build a structure exactly where the thermal contrast is strongest? Instead of making things clearer, the two-tone hemisphere creates more questions. It ties the ridge to a part of the moon that behaves differently from the rest, and that complicates every idea scientists have tried to use to explain it. The ridge isn't just an isolated wall. It sits in a region shaped by dust, heat, and long-term ice movement. And that connection adds another layer to understanding why this feature shouldn't exist in the first place. When scientists first saw the ridge, the instinct was to fit it into familiar geological categories. Icy moons can shift, crack, fold, and reshape themselves under internal forces. Some build long troughs or ridges when the crust expands or contracts. Others show fractures from tidal stress. But none of those processes line up cleanly with what we see here. Tectonic activity usually creates features that stretch across a surface in irregular paths. They might follow patterns set by interior heat or crustal weaknesses, but they don't trace the equator with millimeter-level commitment. And tectonic ridges don't appear as single sharp structures running around an entire world. They break into segments, shift direction, or interact with other fault systems. On this moon, the ridge stays locked to one line with no signs of drifting away from that path. That alone makes a tectonic origin unlikely. As William B. McKinnon of Washington University in St. Louis has pointed out, some people have proposed that the ridge might have been caused by a string of volcanic eruptions, or maybe it's a set of faults. But to align it all perfectly like that, there is just no similar example in the solar system to point to such a thing. Volcanism also doesn't help. Icy volcanism on these kinds of moons produces rounded domes, smooth flows, or broad plains of erupted material. It doesn't create a narrow wall that stretches for more than 1,000 kilometers. There are no signs of vents, channels, or flow patterns near the ridge. The structure rises too steeply, too cleanly, and too evenly for volcanic buildup. If it were an eruptive feature, you would expect evidence of different eruption stages or overlapping sheets of frozen material. But the ridge has none of those signatures. Internal convection, the slow churning of warm ice inside the moon, can push crust upward, forming long belts. But convection-driven belts don't run only along the equator, nor do they maintain a constant width and height across nearly an entire hemisphere. They also tend to form broader, smoother uplifts, not steep peaks with triangular cross-sections. A process strong enough to lift ice to such heights would likely create global deformation, leaving fractures or depressions elsewhere. Those global signs don't exist here. Simulations of plume-driven resurfacing predict chaotic upwellings and polygonal patterns, as seen on Ganymede, along with variable relief that tapers unevenly, contrasting sharply with the ridge's uniform elevations and absence of associated chaos. Another idea is global contraction. When a moon cools, it can shrink and compress its outer shell, creating ridges or folded terrain. But contraction usually produces widespread patterns, not a single structure limited to the equator. And contraction doesn't explain the height of the ridge. A compressional force running around the moon wouldn't stack material into a 20-kilometer wall. You would expect low ridges, broken folds, or scattered elevated zones. Instead, the ridge is tall, narrow, and continuous. What ties all these failures together is a simple fact. Natural internal processes do not select the equator with such precision. They also don't produce tall, sharp, evenly formed peaks that stand unchanged for billions of years without similar features appearing elsewhere. Any viable model must satisfy three critical observations: why the feature sits precisely on the equator, why it is confined only to the equator, and why only Iapetus possesses such a ridge. The ridge behaves like a structure built by a mechanism that targeted one specific line on the moon and deposited or shaped material in a consistent way along that path. The absence of matching geological signatures leaves a gap. The ridge doesn't fit the normal tools we use to describe how moons evolve. And once you rule out the familiar, you're forced to look at explanations that involve early conditions, external influences, or combinations of events that rarely happen in the solar system. Especially given that no other icy moon, from the active Enceladus to the ancient Callisto, exhibits an equatorial-only analog despite shared histories of tidal heating and bombardment. Once internal processes started failing to explain the ridge, attention shifted to something simpler. What if the ridge didn't come from inside the moon at all? The idea that the moon might have once had a ring sounds unusual, but it fits the mechanical behavior of small bodies with enough mass to capture debris. If a large impact created a cloud of material around the moon, part of that debris could have spread into a thin disk. Anything that moved inside the moon's Roche limit would have been torn apart, forming a ring that circled the moon's equator. A ring like that wouldn't last long. Over time, debris in low orbit gradually falls inward. And when it falls, it doesn't scatter across the surface. It lands along the equator where its orbital path was. The ridge's continuous line matches this perfectly. You only need a process that drops material along one line for an extended period. Imagine all of these particles coming down horizontally across the equatorial surface at about 400 meters per second, the speed of a rifle bullet, one after the other, like frozen baseballs, says planetary scientist William B. McKinnon. Particles would impact one by one, over and over again on the equatorial line. At first, the debris would have made holes to form a groove that eventually filled up. The ridge behaves exactly like something built by accumulation, not uplift. Next is the ridge's shape. Many peaks have a triangular cross-section, which is typical of loose material stacking under its own weight. When debris falls repeatedly in the same place, it builds a slope up to a natural limit. The ridge's slopes match that limit closely. This isn't what you get from crust being pushed upward. Pushed crust breaks, fractures, and folds. The ridge shows none of that. Instead, it looks like something formed by slow but steady deposits piling up over time. Cassini images also show sections where debris seems to have slumped down the sides, leaving long streaks that look like landslides. That's exactly what you'd expect if the ridge were a massive pile of material settled along the equator. Landslides make sense when you have loose or semi-loose deposits sitting on steep slopes. They do not make sense if the ridge were a hard tectonic uplift frozen in place. An uplift would crack when stressed. A debris pile shifts, slumps, and softens over billions of years. The ridge shows behavior closer to the second case. Another strength of the ring collapse idea is the precision of the equatorial alignment. Material falling from orbit does not pick random latitudes. It follows the plane of its orbit. As planetary scientist Andrew Dombard explains, when you have a debris ring around a body, the collisional interactions steal energy out of the orbit. And the lowest energy state that a body can be in is right over the rotational bulge of a planetary body, the equator. That's why the rings of Jupiter, Saturn, Uranus, and Neptune are over the equator. If the Moon once hosted a ring aligned with its equator, the debris would have settled straight down onto the equator itself. That solves one of the biggest problems faced by internal models. No geological process naturally picks the equator as a target. Orbiting debris does. There is still the question of origin. Where did the ring come from? The most likely cause is a major impact early in the Moon's history, one strong enough to throw material into orbit. After the impact, the debris could spread out, settle into a ring, and then rain down over time. That timeline matches the ridge's great age and explains why the structure appears ancient and heavily cratered. The ring collapse idea doesn't answer everything, but it succeeds where internal models fail. It explains the ridge's narrow width, sharp peaks, continuous path, and perfect alignment. It also matches the slope angles and the signs of long-term movement on the sides. It turns the ridge from a geological puzzle into something that emerges naturally when orbiting material loses energy and falls back onto a surface. The simplicity of the process is part of what makes it compelling. The ring collapse idea solves many problems, but scientists eventually realized that a ring alone might not explain everything about the ridge. That led to a more complete model built around an early impact. Proposed by some scientists, this scenario posits that a giant impact created not only a debris disk but also a temporary subsatellite, a small moon formed from the ejected material. This subsatellite doesn't stay forever. It circles the main moon and slowly moves outward as tidal forces act on both bodies. At the same time, it affects the inner ring through its gravity. As the subsatellite moves, its pull helps spread the ring and drive the inner material inward, where it eventually falls onto the surface. That steady drop of debris builds the ridge, matching the long, narrow structure that we see today. The role of the subsatellite is important because it adds something the simple ring idea cannot: a way to explain the moon's slow rotation. A world that shows signs of an early fast spin should have taken a long time to slow down by tidal forces alone. But if a small companion moon existed for a period of time, the gravitational interaction between the two would have removed rotational energy more quickly. This fits with the moon's distorted shape, which suggests it once spun much faster. It gives the system a way to lose that spin early, before the ridge is covered in countless impacts. The model also helps explain the ridge's consistency. A ring influenced by a subsatellite would likely drop material more evenly over time, applying a steady supply of debris along the equator. That could create the near-continuous line we see today. The triangular shape of many peaks also fits well with the idea of repeated deposits stacking on top of older layers. A crucial piece of evidence supporting this model is the moon's unusually large hill sphere, the region where its gravity dominates over Saturn's. Among major Saturnian moons, only Iapetus possesses a hill sphere large enough to have stably hosted a subsatellite long enough for tidal decay to deliver the required debris. Only the moon could have had the orbital space for the subsatellite to then evolve and come down toward its surface and break up and supply the ridge. Another strength of this scenario is its timing. A giant impact early in the solar system's history is entirely realistic. Many moons and planets experienced similar events. The formation of a temporary subsatellite is also plausible since small bodies can gather loose debris quickly and just as quickly lose stability once external forces take over. The Moon's current lack of such a companion doesn't contradict the idea. The subsatellite would have been lost long ago, either by crashing into the main Moon or by drifting outward until it escaped. There are still uncertainties. The exact behavior of ring debris under long-term tidal influence is difficult to simulate perfectly. Planetary scientists acknowledge that while extensive corroborating calculations exist, rigorous end-to-end dynamical simulations of the entire process remain a future goal. The shape of the ridge suggests a long accumulation period, but not enough detail survives to show whether the deposition was constant or occurred in bursts. And while this model explains more features than earlier ideas, it is still built on early conditions that can't be observed directly. Even with these gaps, the giant impact plus subsatellite scenario remains one of the strongest explanations because it ties together several features that once looked unrelated. It provides a source of material, a mechanism to drop that material onto the equator, and a way to slow the Moon's rotation during the same period. No internal model offers that combination, which is why, since the early 2000s, this family of exogenic models has become the leading explanation among planetary scientists for both the ridge and the Moon's extreme equatorial bulge. The ridge isn't just a strange feature sitting on a normal moon. It changes how scientists understand the entire object. Most moons with a smooth, round shape are in what's called hydrostatic equilibrium. Their rotation and internal structure naturally settle into a balanced form. But Iapetus doesn't follow that pattern. Its equator is wider than expected, its poles are slightly flattened, and its overall shape looks as if it was locked into place when the Moon was in a very different state. The ridge adds another layer to this odd geometry. If the Moon once spun faster, its shape would have bulged outward around the equator. That part does match what we see. But the ridge sits on top of an already widened region, making the equatorial zone even more prominent. It acts like a raised edge along the middle of the Moon, exaggerating the bulge rather than smoothing it. This suggests that whatever shaped the ridge also interacted with the Moon's early spin, or at least arrived at a time when the Moon's structure was still settling. Another clue comes from how the ridge lines up with the overall geometry. The Moon's equator is not just a line across its surface. It's a structural boundary that reflects the Moon's early rotation. For the ridge to sit exactly on that boundary, its formation mechanism had to be tied to the Moon's rotational history. Internal tectonics rarely lock onto such precise global markers, but orbiting debris does. The ridge's placement, therefore, connects a surface structure to the deeper story of how the Moon evolved. The combination of a wide equator, flattened poles, and a sharp equatorial ridge points toward a past where the Moon's shape was determined early and then preserved for billions of years. That preservation means the Moon cooled quickly, stiffening its outer layers before later processes could erase or modify the structure. This makes the ridge not just a feature on the surface, but a snapshot of the Moon's earliest physical state. Another important detail is how stable the ridge has remained. Even after billions of years of impacts and changes in surface conditions, it still stands tall. That endurance suggests that the bulk of the ridge was already solid or compacted early on. A process involving falling debris or a combination of debris and early spin conditions could have created a stable base that held together long after the ring or subsatellite disappeared. Looking at the ridge in context, it becomes clear that it isn't just an isolated mystery. It is part of a wider pattern that shows Iapetus formed in an environment where rotation, cooling, and external impacts were all playing significant roles. The ridge reinforces the idea that this moon had an active and complicated early history, and that many of its present traits were shaped during a relatively short period. Instead of seeing the moon as a simple, icy world, the ridge forces scientists to consider a more dynamic formation story. Everything we know about this ridge comes from a brief flyby. Cassini passed the moon only once at close range, gathering a snapshot rather than a full survey. That single opportunity produced enough questions to keep scientists busy for years, but it also left large gaps. Many parts of the ridge were seen at low resolution. The depth of its valleys, the true shape of its peaks, and the fine details of its slopes are still not fully mapped. A future spacecraft with modern imaging equipment could fill those gaps quickly. One of the most important missing pieces is information about the moon's interior. We still do not know how thick the crust is, how rigid it became over time, or whether there are layers beneath the surface that played a role in shaping the ridge. A spacecraft equipped with instruments that measure gravity variations or use radar to probe beneath the crust could tell us whether the ridge sits on top of buried structures, or if it stands entirely on accumulated material. Right now, those details are hidden. Another major goal for a future mission would be precise sampling of the surface. If the ridge was built by falling debris, the material along its slopes might carry chemical signatures that differ from deeper terrain. A lander or a close-range spectrometer could detect whether the ridge consists of loose, mixed particles or a more uniform layer consistent with internal uplift. Even small differences in grain size or composition would help narrow down which models still make sense. High-resolution mapping would also help explain why the ridge is uneven. Some sections of the ridge are tall and sharp, while others fade or appear broken. With better images, scientists could examine these transitions and see whether they were shaped by variations in debris flow, shifts in the early ring, or later erosion. The patterns along the ridge may contain clues about the sequence of events that built it. A mission could also clarify the connection between the ridge and the dark hemisphere. The coating that makes one side of the moon dark still raises questions about timing. If a spacecraft analyzed how thick that coating is around the ridge and how its chemistry changes with location, we might be able to finally decide whether the ridge formed before or after the two-tone surface appeared. That single detail would eliminate entire categories of theories. Finally, a dedicated mission would allow long-term monitoring. Changes in temperature, small movements along the slopes, or tiny shifts in material could reveal how stable the ridge truly is today. Even slight variations could tell us whether the ridge is still adjusting under its own weight or whether it has been frozen solid for most of its life. Until a spacecraft returns, the ridge will remain a partly answered mystery. Cassini gave us a glimpse, but not the full picture. A future mission could turn that glimpse into a complete understanding, showing precisely how a moon this small ended up with a feature that still challenges our expectations.